Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too with worldwide data centers, including new ones in Toronto and Mumbai. And for your machine learning workloads, they just announced dedicated CPU instances. Go to dataengineeringpodcast.com/Linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, and the Open Data Science Conference, with upcoming events including the O'Reilly AI Conference, the Strata Data Conference, and the combined events of the Data Architecture Summit and Graph Forum. Go to dataengineeringpodcast.com/conferences to learn more and to take advantage of our partner discounts when you register. Your host is Tobias Macy, and today I'm interviewing Flavio Villanustre about the HPCC project and his work at LexisNexis Risk Solutions. So, Flavio, can you start by introducing yourself?
Of course, Tobias. My name is Flavio Villanustre. I'm Vice President of Technology and CISO for LexisNexis Risk Solutions. In LexisNexis Risk Solutions, we have a data platform called the HPCC Systems platform. We have made that platform open source in 2011, and since then, I've been also, as part of my role, involved with leading the open source community initiative. Ensuring that the open source community truly leverages the platform, helps contribute to the platform, and certainly creating a liaison between the LexisNexis Risk Solutions organization and the rest of the larger open source community.
And do you remember how you first got involved in the area of data management?
Probably it has been seamless, and it's probably in the early 90s, been going through the database to the database analytics to data management to data integration. Keep in mind that even within LexisNexis, we started the HPC Systems platform back earlier, before year 2000. So back then, we already had data management challenges with traditional platforms, and we started with this. And I've been involved since I joined the company in 2002, just with HPCC. But before, I've been in data management for a very long time.
And so for the HPCC system itself, can you talk through some of the problems that it was designed to solve and some of the issues that you were facing at LexisNexis that led to its original creation?
Oh, absolutely. So in LexisNexis Risk Solutions, we started with risk management as our core competency back in the mid 90s. And as we got into risk management, one of the core assets when you are trying to assess risk and predict outcomes is data. Even before people spoke about big data, we had a significant amount of data, mostly structured, some unstructured data too, but the vast majority structured. And we used to use the traditional platforms out there, whatever we could get our hands on. And again, this is all back in the day before Hadoop and before MapReduce was applied as a distributed paradigm for data management or anything like that. Databases, Sybase, Oracle, whatever it was, Microsoft SQL, data management platforms, Ab initio, Informatica, whatever was available at the time. And certainly the biggest problem we had was scalability. Well, it was twofold. One was scalability. All of those solutions typically run in a single system. So there is a limit to how much bigger you can go vertically. And certainly, if you are trying to also consider cost affordability of the system, and that limit is much lower as well, right? There is a point where you go beyond what the commodity system is, and you start paying a premium price for whatever it is. So that was the first piece. So one of the attempts at solving this problem was to split the data and use different systems. But splitting the data creates also challenges around data integration. If you're trying to link data, surely you can take the traditional approach, which is you segment your data into tables, and you put those tables in different databases, and then use some sort of foreign key to join the data. But that's all good and dandy as long as you have a foreign key that is unique and that is reliable. And that's not the case with data that you acquire from the outside. If you generate the data, you can have that. If you bring the data from the outside, you might have a record that says this record is about John Smith, and you might have another record that says this record is about John Smith. But do you know for sure if these two records are about the same John Smith? And that's a linking problem. And the only way that you can do linking effectively is to put all the data together. And now we had this particular issue where, in order to scale, we need to segment the data. In order to be able to do what we need to do, we need to put the data in the same data lake, as a term came later. We used to call this data land. Eventually, we changed the term in the late 2000s because data lake became more well known. So at that point, the potential paths to overcome the challenge where, well, we either split all of the data as we were saying before, and then we come up with some sort of a meta system that will leverage all of these distributed data stores, and potentially when you're doing probabilistic linkage, you have problems that are of the computational complexity O square or worse. So that means that we will pay a significant price in performance, but potentially can be done if you have enough time and your systems are big enough and you have enough bandwidth in between the systems. But the complexity that you're gaining from a programming standpoint is also quite significant. And sometimes you don't have enough time. Sometimes you get data updates that are maybe hourly or daily. And doing this big linking process might take you weeks or months if you're doing this across different systems. So, and the complexity in programming this is also a pretty significant factor to consider. So, at that point, we thought that maybe a better approach to this was to create sort of an underlying platform to apply this type of solutions to problems, these algorithms, in a divide and conquer type of approach. We would have something that would partition the data automatically, and that would distribute the data in partitions into different commodity computers. And then we would add an abstraction layer on top of it that would create a programming interface that gave you the appearance that you were dealing with a single system with a single data store, and whatever you coded for that data store would be automatically distributed to the underlying partitions. We would also, because of the way the hardware was far slower than it is today, we thought that a good idea would be to move also as much of the algorithm as we could to those partitions rather than executing this centrally. So instead of bringing all of the data to a single place to process this, which the single place might not have enough capacity, would be to do as much as you can, for example, a pre-filter operation or a distributed grouping operation or distributed filtering operation across each one of the partitions. And eventually, once you need to do the global aggregation, you can do it centrally, but now with a far smaller data set that is already pre-filtered. And the time came to define how to build the abstraction layer. The one thing that we knew about was SQL as a programming language, and we said, well, this must be something that we can tackle with SQL as a programming interface for our data analysts. But they were quite used to a data flow model because of the type of tools that they were using before. Things like, for example, ab initio, where the data flows are these diagrams where your nodes are the operations, so the activities that you do on the data, and the lines connecting the flow, the activities represent the data traversing those. So we thought that a better approach than SQL would be to create a language that gave you the ability to build this sort of data flows in that system. And that's how ECL was born, which is the language that runs on top of HPCC and HPCC.
So it's interesting that you had all of these very forward-looking ideas in terms of how to approach data management well in advance of when the overall industry started to encounter the same types of problems as far as the size and scope of the data that they were dealing with, that led to the rise of the Hadoop ecosystem and the overall ideas around data lakes and MapReduce and some of the new data management paradigms that have come up. And I'm wondering what the overall landscape looked like in the early days of building the HPCC system that required you to implement this in-house, and some of the other systems or ideas that you drew on for inspiration for some of these approaches towards the data management and the overall systems architecture for HPCC.
That is a great question. So it's interesting because in the early days, when we told people what we were doing, they would look us puzzled and ask, well, why don't you use database XYZ or data management system XYZ. The reality is that none of those would be able to cope with the type of data frequent data process. It wouldn't offer the flexibility of the process like this probabilistic record linkage that I explained before that we do, and certainly wouldn't offer a seamless transition between data management and data querying, which was also one of the important requirements that we had at the time. It was quite difficult to explain to others why we were doing this and what we were gaining by doing this. So map and reduce operations as functional programming operations have been around for a very long time, since the least days in the 50s. But the idea of using map and reduce as operations for distributed data management didn't get published until this, I think, was September or December 2004. And I remember reading the original paper from the Google researchers and thinking, well, now someone else has the same problem and they are doing something about it. Even though at the time we already had HPC and we already had ECL, so it was perhaps too late to go back and try to re-implement the data management aspects and the programming layer abstraction on HPCC. So just for those people in the audience that don't know much about ECL, and again, this is all open source, so open source and free Apache 2 license, and there are no strings attached. So please go there and look at it. But in summary, ECL is a declarative data flow programming language, and not unlike in the declarative manner what you can find in SQL or functional programming languages, Haskell, maybe ways of programming Lisp and Clojure and other programming languages out there. But it's data flow. From that standpoint, it's closer to something like TensorFlow, if you are familiar with TensorFlow as a deep learning programming paradigm and framework. So where you code data operations, there are primitives that are data primitives, like for example sort. You can say sort data set by this column in this order, and then you can add more modifiers if you want. You can do a join across data sets, and again the operation is join. And you can do a roll up operation, and the operation is named roll up. All of these are high level operations. You define them in your program, and in a declarative programming language you create definitions rather than assign variables. For those that are not familiar with declarative programming, and I assume many are in this audience, declarative programming has, for the most part, the property of having immutable data structures, which doesn't mean that you cannot do valuable work and you can do all of the work the same way or better, but it gets rid of side effects and other pretty bad issues with more traditional mutable data structures. So you define attributes, you define things. I have a data set that has a phone book, and I want to define an attribute that is this data set filtered by a particular variable. And then I might define another attribute that uses the filter data set to now group it in a particular way. So at the end of the day, an ECL program is just a set of definitions that are compiled by an ECL compiler, and this compiles ECL into C, which then, or in reality C++, which then goes into the C++ compiler of the system, GCC or Clang or whatever you have, and generates assembly code. And that is the code that is run in the platform. But the fact that ECL is such a high-level programming language, and the fact that it's declarative, means that the ECL compiler can take decisions that otherwise more imperative type of programming language wouldn't allow the compiler to take. The compiler in a declarative programming language, and functional programming languages is also the same case, knows the ultimate goal of the program, because the program in some ways isomorphic to an equation, and you could inline from a functional standpoint every one of your statements into a single massive statement, which you of course don't do from a clarity standpoint. But the compiler can now, for example, do things like apply non-strictness. If you put a statement, if you made a definition that is never going to be used, there is no point for that definition to be even compiled in or executed at all. That saves performance. You could, if you have a conditional fork in a place in your code, but that condition is always met or never met, then there is no need to compile the other branch. All of this gives you performance implications that can be far more significant when you're dealing with big data. One of the particular optimizations can be around data encapsulation. It is a lot far it's far more efficient and it's a lot faster if you are going to do several operations through a very large data set to combine all of those operations and do only one pass on the data with all the operations if it's possible. And the ECL compiler does exactly that, and takes away a little bit of the perhaps flexibility on the programmer by making it far more intelligent at the moment it's compiled. Of course, programmers can tell the compiler, "I know better," and force it to do something that might be otherwise unreasonable. But just an example, you could say, "Well, I want to sort this data set, and then I want to filter it out and get only these few records." And if you say that in that order, an imperative programming language would first sort, and sort even in the most optimal case is an n log n type of operation and computational complexity, and then filter out and get only a few records out of it, when the optimal situation would be to filter it out first and get those few records and then sort those records. And the ECL compiler does exactly that.
The fact that the language that you're using for defining these manipulations ends up being compiled, and I know that it's implemented in C and C++, both the ECL language itself as well as the overall HPCC platform, is definitely a great opportunity for better performance characteristics. And I know that in the comparisons that you have available for going between HPCC and Hadoop, that's one of the things that gets called out. And as far as the overall workflow for somebody who is interacting with the system using that ECL language, I'm curious if the compilation step ends up being in any way not a hindrance, but a delaying factor as far as being able to do some experimental iteration, or if there is the capability of doing some level of interactive analysis or interaction with the data for being able to determine what is the appropriate set of statements to be able to get the desired end result when you're building an ECL data flow.
That is another great question. I can see that you are quite versed in programming. So you're right. The fact that ECL is compiled means that, just to, again, for the rest of the audience, we have an integrated development environment called ECL ID, and of course we support others like Eclipse and Visual Studio and all of the standard ones. But I'll just talk about ECL ID because it's what I mostly use. In that case, when you write code, you write the ECL code, and then you can certainly run the test of the code, verify that that code is correct syntactically. But at some point, you want to run the code because you want to you want to know if semantically it makes sense and it will give you the right results, right? So, and running the code will go through the compilation process. Depending on how large your code base is, certainly the compilation process can take longer. Now, the compiler does know what hasn't been modified. Remember, again, ACL is a declarative programming language. So if you haven't touched a number of attributes, again, data structures are immutable, and attributes that don't change, since there are no side effects, should be exactly the same. So the fact that when you define a function, that function has referential transparency, that means that if you call that function at any time, it would give you the correct result or the same result based on the parameter and just based on the parameter that you're passing. With that, the compiler can take some shortcuts. And if you are recompiling some bunch of ECL attributes, but you haven't touched many of them, it will just use the precompiled code for those and only compile those that you have changed. So the compilation process, when you are iteratively working on code, tends to be fairly quick, maybe a few seconds. Of course, you depend on having an ECL compiler available. Traditionally, we used to have a centralized approach to the ECL compiler where it would be one or a few of them running in the system. We have moved to a more distributed model where when you deploy your ECL ID and your ECL tools in your workstation, there is a compiler that goes there. So the ECL compilation process can happen in the workstation as well, and that gives you and the ability to have it available for you at all times when you're trying to use it. One of the bottlenecks was at some point before when you were trying to do this quick iterative programming approach to things, and the compiler was being used by someone that was compiling a massive amount of ECL code from some completely new job, and might have taken minutes, and you were just there sitting picking your nose, waiting for the compiler to finish that one compilation. But the time to compile is an extremely important consideration, and we continuously improve the compiler to make it faster. We have learned, you can imagine, over the. By the way, some of the same core developers that developed the ECL compiler, Gavin Halliday, for example, have been with us since the very beginning. He was one of the core architects behind the initial design of the platform, and he's still the lead architect that is developing that ECL compiler, which means that a lot of the knowledge that has come into the compiler process and to optimizing it is still getting better and better. Of course, now with a larger community working on the compiler and more people involved and more documentation around it, means that others can pick up where he lives. But hopefully, he will be around and doing this for a very long time, and making sure that the compiler is as just in time as it can be is very. There is no at this point interpreters for ECL, and I think it would be quite difficult to make it completely interactive, where the point where you submit just a line of code and does something, because of the way a declarative programming paradigm works, right?
And also because of the fact that you're working most likely with large volumes of data distributed across multiple nodes, being able to do a REPL driven development is not really very practical, or and it doesn't really make a lot of sense. But the fact that there is this fast compilation step and the ability to have a near real-time interactivity as far as seeing what the output of your programming is. It's good to see, particularly in the big data landscape, where I know that the overall MapReduce paradigm was plagued in the early years by the fact that it was such a time-consuming process to submit a job and then see what the output was before you could then take that feedback and wrap that into your next attempt. And that's why there have been so many different layers added on top of the Hadoop platform in the form of Pig and Hive and various SQL interfaces to be able to get a more real-time and interactive and iterative development cycle built in.
Yeah, and you're absolutely right there. Now, one thing that I haven't told the audience yet is how the platform looks like, and I think that's this. We are getting to the point where it's quite important to explain that there are two main components in the HPC Systems platform. There is one component that does data integration. There's this massive data management engine, equivalent to your data lake management system, which is called Thor. Thor is meant to run one ECL work unit at a time, which a work unit can consist of a large number of operations, and many of them are done in parallel, of course. And there is another one which is known as Roxy, which is the data delivery engine. There is one which is a sort of a hybrid called H-Thor. Now, Roxy and H-Thor both are designed to operate in tens of thousands or more operations at the same time, simultaneously. Thor is meant to do one work unit at a time. So when you are developing on Thor, even though your compilation process might be quick and you might run on small data sets quickly because you can execute this work unit on those little data sets using, for example, H-Thor. If you are trying to do the large data transformation over large data sets in your Thor system, you still need to go to the queue in that Thor, and you will get your time whenever it's due for you, right? Surely you can. We have priority, so you can jump into a higher priority queue, and maybe you can be queued after just the current job, but before any other future jobs. We also partition jobs into smaller units, and those smaller units can be also segmented. They are fairly independent from each other, so we could even interleave some of your jobs into in between a job that is running by getting it into each one of those segments of the work unit. But still, the interactiveness there is a little bit less than optimal. But it is the nature of the beast. It's because you want to have a large system to be able to process this throughout all the data in a relatively fast manner. If we were trying to truly multi-process there, most likely many of the resources available could suffer. So you might end up paying a significant overhead across all of the processes that are running in parallel. Now, I did say that Thor ran only one work unit at a time, but that was a little bit of a lie. That was really a few years ago. Today, it does run. You can define multiple queues in a Thor, and you can make it run 3, 4, 10 work units, but certainly not thousands of them. So that's a big difference between that and Roxy. Can you run your work unit on Roxy? Yes, or in H Thor, and that will run concurrently with anything else that is running, with almost no limit there. Thousands and thousands of them can run at the same time, but there are other considerations on when you run things on Roxy or H-Thor versus in Thor. So it might not be what you really want.
Taking that a bit further, can you talk through a standard workflow for somebody who has some data problem that they're trying to solve and the overall life cycle of the information as it starts from the source system, gets loaded into the storage layer for the HPCC platform. They define an ECL job for it that then gets executed in Thor, HThor, and then being able to query it out the other end from Roxy, and just the overall systems that get interacted with at each stage of that data lifecycle.
Oh, I'd love to. So, very well, let's set up something very simple as an example. You have a number of data sets that are coming from the outside. You need to load those data sets into HPCC. So, the first operation that happens is something that is known as spray. Spray is simple process is and spray comes from the concept of spray painting the data across the cluster, right? So this runs on a Windows box or on a Linux box, and we'll take the data set. Let's say that your data set is, just give a number, 1 million records long. It will, and your data set can be in any format, CSV or any other, or fixed length, delimited, or whatever. So it will look at your total data set. It will look at the size of the Thor cluster where the data will reside initially for processing. And let's say that you have 1 million records in your data set and you have 10 nodes on your Thor. Let's just make round numbers and small numbers. So it will partition the data set into 10 partitions because you have 10 nodes, and it will then just copy, transfer each one of those partitions to the corresponding to Thor node. This is done if it can be parallelized in some way, because, for example, your data is fixed length, it will automatically use pointers and parallelize this. If the data is, I don't know, an XML format or delimited format where it's very hard to find the partition points, it will need to do a pass on the data, find the partition points, and eventually do the parallel copying to the Thor system. So now you will end up with 10 partitions of the data, with the data in no particular ordering other than the ordering that you had before, right? So the first 100,000 records will go to the first node, the second 100,000 records will go to the second node, and so on and so forth until you go to the end of the data set. This puts each one of the nodes in a similar amount of records per node, which tends to be a good thing for most processes. Once the data is sprayed, or while the data has been sprayed, depending on the length of the data, or even before, yeah, you will most likely need to write a work unit to work on the data. And I'm trying to do this example in a way that is the data, the first time you see that data. So otherwise, all of this is automated, right? So you don't need to do anything manually. All of this is scheduled and automated, and the work unit that you already had will run on the new data set and will append it or whatever needs to be done. But let's imagine that it's completely new. So now you write your work unit, and let's say that your data set was a phone book, and you want to, first of all, eliminate duplicates, build some roll up views on that phone book, and eventually you want to allow the users to run some queries on a web interface to look up people in the phone book. So you and let's just for the sake of an argument, let's say that you're also trying to join that phone book with your customer contact information. So you will write a work unit that will have that join to merge those two, and you will have some deduplication and perhaps some sorting. And after you have that, you will need to build. You will want. You don't need to, but you will want to build some keys. There is another again key build process in Thor. All this runs on Thor. That will be part of your work unit. So essentially, it's all ECL. write that work unit in ECL, submit that work unit, the ECL will be compiled, will run on your data. Hopefully, the ECL will be syntactically correct when you submit it, and it will run with giving you the results that you were expecting on that data. ECL is, I didn't mention this before, but it's a statically typed language as well, which means that it is a little bit harder to have errors that will only appear in runtime. Between the fact that it has no side effects and that it's statically typed, most typing errors, type errors, type matching errors, and type matching to function operations errors are a lot less frequent there. It's not like Python that it might seem okay. The run might be fine, but then one run at some point it will give you some weird error because a variable that was supposed to have a piece of text has a number or vice versa. So you run the work unit will give you the result. As a result of this work unit will potentially give you some statistics on the data, some metrics, and it will give you a number of keys. Those keys will be also partitioned in Thor, so there will be still 10 nodes. The keys will be partitioned in 10 pieces in those nodes, and you will be able to query those keys as well from Thor. So you can write a few attributes that can do the querying there. But at some point, you will want to write those queries for Roxy to use, and you will want to put that data in Roxy because you don't have one user querying the data. You will have a million users going to query that data, and perhaps 10,000 of them will be simultaneously querying. So for that process, you write another piece of ECL, another sort of work unit, but we call this query, and you submit that to Roxy instead of Thor. And there is a slightly different way to submit it to Roxy. So you select Roxy and you submit this. The difference between this query and the work unit that you had in Thor is that the query is parameterized. And similar to parameterized store procedure in your database, you will define some variables that are supposed to be coming from the front end, from the input from the user. And then you just use the values on those variables to run some of the whatever filters or aggregations that you need to do there, which will work in Roxy and will leverage the keys that you had from Thor. I said before, the keys are not mandatory. Roxy can perfectly work without keys, and it even has a way to work with in-memory distributed data sets as well. So even if you don't have a key, you don't pay a significant price in the lookups by doing this sequential lookup on the data and the full table scans of your database. So you submit that to Roxy. When you submit that query to Roxy, Roxy will realize that it has the data is not in Roxy, it's in Thor, and this is also your choice, but most likely you will just tell Roxy to load that data from Thor. It will know where to load the data from because it knows where the keys are and what the names of those keys are. It will automatically load those keys. And also it's your choice to tell Roxy to start allowing users to query the front-end interface or to, while it's loading the data, or to wait until the data is loaded before it allows the queries to happen. The moment you submit the query to Roxy, Roxy will automatically expose on the front end, there is a component called ESP. That component called ESP exposes a web services interface. And this gives you a RESTful interface, a SOAP interface, a JSON for the payload if you go for the RESTful interface, even an ODBC interface if you want. So you can have even SQL on the front end. So the moment you submit the query automatically auto-generates this all of these web service interfaces. So automatically, if you want to go with a web browser on the front end, or if you have an application that can use, I don't know, a RESTful interface over HTTP or HTTPS, you can use that and it will automatically have access to that Roxy query that you submitted. Of course, a single Roxy might have not one query, but 1,000 different queries at the same time. All of them listening on the interface, and it can have several versions of the queries as well. The queries are all exposed version from the front end, so you know what the users are accessing. And if you are deploying a new version of a query or modifying an existing query, you don't break your users if you don't want to. You give them the ability to migrate to the new version as they want. And that's it. That's pretty much the process. Now, as you add complexity to this, well, you need to have automation. All of this can be fully automated in ECL. You might want to have data updates. And I told you data is immutable. So every time you think you're mutating data, you're updating data set, you're really creating a new data set, which is good because it gives you full provenance. You can go back to your every data version. Of course, at some point you need to delete data or you will run out of space, and that can be also automated. And if you have updates on your data, we have concepts like super files where you can apply updates, which are essentially new overlays on the existing data, and the existing work unit can just work on that happily as if it was a single data set. So a lot of these complexities in the that otherwise will be exposed to the user, to the developer, are all abstracted out by the system. So the developers, if they don't want to see the underlying complexities, they don't need to. If they do, they have the ability to do that. I mentioned before, well, ECL will optimize things. If you tell it, do this join, but before doing the join, do the sort. Well, it might know that it needs to do the sort, so the sort won't be done. But if you know that your data is already sorted, you might say, well, let's not do the sort. I want to do this join in each one of the partitions locally instead of a global join. And or the same thing with the sort operation. And ECL, of course, if you tell it to do that and you know better than the system, ECL will follow your orders. If not, it will take the safe approach to your operation, even if it's a little bit more overhead, of course.
A couple of things that I'm curious about out of this are the storage layer of the HPCC platform and some of the ways that you manage redundancy and durability of the data. And I also noticed when looking through documentation that there is some support for being able to take backups of the information, which I know is something that is non trivial when dealing with large volumes. And also on the Roxy side, I know that it maintains an index of the data, and I'm curious how that index is represented and maintained and kept up to date in the overall life cycle of the platform.
Those are also very good questions. So in the case of Thor has a concept. So we need to go down to a little bit of the system architecture. So in Thor, you have each one of these nodes that handle primarily their chunk of data, their partition of the data. But there is always a body node, some other node that has also their own partition, but they have a copy of the partition of some other node. If you have 10 nodes in your cluster, your node number one might have the first partition and might have a copy of the partition that node 10 has. Node number two might have the partition number two, but also might have a copy of the partition that node number one has, and so on and so forth. Every node would have one primary partition and one backup partition of the other node. Every time you run a work unit, I said that the data is immutable, but you are generating a new data set every time that you are materializing data on the system, either by forcing it to materialize or by letting the system materialize the data when it's necessary. And the system tries to stream as much in this ways more similar to Spark or TensorFlow, where the data can be streamed from activity to activity without being materialized, unlike MapReduce. And at some point, it decides that it's the time to materialize because the next operation might require materialized data, or because you've been going for too long with data that if something goes wrong with the system will be blown up. Where every time it materializes data, there is a lazy copy happening with the new data that is materialized to this backup node. So surely there could be a point where something goes very wrong and one of the nodes dies and the data in that disk is corrupted, but you know that you have always another node that has that copy, and the moment you do what is known as kung fu, essentially pull it out, put another one in, the system will automatically rebuild that missing partition because it has a complete redundancy of all of the data partitions always in a different node. In the case of Roxy, so in the case of Thor, this seems to be sufficient. There is, of course, the ability to do backups, and you can back up all of these partitions, which are just files in the Linux file system. So you can even back them up using any Linux backup utility, or you can use HPC to do the backups for you into any other system. You can have cold storage. Some of the problems is what happens is when your data center is compromised, and now someone modified or destroyed the data in live system. So you may want to have some sort of offline backup, and you can all handle this in the normal system backup configuration, or you can do it with HPC and make it offload the data as well. But for Roxy, the redundancy is even more critical. In the case of Thor, when a node dies, it is sometimes less convenient to let the system work in a degraded way, because the system is typically as fast as the slowest node. If all nodes are doing the same amount of work, a process that takes an hour will take an hour. But if you happen to have one node that died, and now there is one node that is doing twice the work because it has to deal with two partitions of data, its own and the backup of the other one, the time to do that process might take 2 hours. So it is more convenient to just stop the process when something like that happens, replace the node, and let the system rebuild that node quickly and continue doing the processing. And that might take an hour and 20 minutes or 10 minutes rather than the 2 hours that otherwise it would have taken. And besides, if a system continues to run and your storage system died in one node because it's old, and there is a chance that other storage systems, when they get under the same stress, will die the same way, you want to replace that one quickly and have a redundant copy as soon as you can, to not run the risk that you lose two of the partitions. And if you lose two partitions that are in different nodes that are not the backup of each other, that's fine. But if you lose the primary node and the backup node for that one, there is a chance that you might end up losing the entire partition, which is bad. Again, bad if you don't have a backup, and even restoring a backup sometimes takes time, so it's also inconvenient. Now, in the Roxy case, you have a far larger pressure to have the process continue, because your Roxy system is typically exposed to online production customers that might pay you a lot of money for you to be highly available. So Roxy allows you to have defined the amount of redundancy that you want. Based on the number of copies that you want, you could say, well, I have a 10 node Roxy and I just need, which is the default, one copy of the data, or I need 3 copies of the data. So maybe the partition in node 1 will have a copy in node 2, node 3, and node 4, and so on and so forth. Of course, you need 4 times the space, but you have a far higher resilience if something goes very wrong. And Roxy will continue to work even if a node is down, or 2 nodes are down, or as many nodes as you want are down, as long as you have the data still fine. Of course, worst case scenario, even if you lose a partition completely, Roxy might, if you want, it might continue to run, but it won't be able to answer any queries that are trying to leverage that particular partition that is gone, which is sometimes not a good situation. When you ask about the format on the keys, and the format of the keys of the indexes in Roxy is interesting, because those keys, which is again typically the format of the data that you have in Roxy, for the most part, you will have a primary key. These are all keys that are multi-field, like in a normal, decent database out there. So they have multiple fields. They go typically. Those fields are ordered by cardinality. So the fields with the larger cardinality will be at the front to make it more better performing. It has interesting abilities, like for example, it can step over a field that you don't have. You have a wildcard for, and still use the remaining fields, which is not something that normally a database doesn't do. Once you have a field that you don't have a value to apply, the rest of the fields on the right hand side are useless. So Roxy has other things that are quite interesting there. But the way the data is stored in those keys is by decomposing those keys into two components. There is a top level component that indicates which node will have that partition, and there is a bottom level component which indicates where in the hard drive of that node the specific data element is, or the specific block of data elements are. So by decomposing the keys in these two hierarchical levels, it means that every node in Roxy can have the top level of that, which is very small. So every node can know where to contact the specific values. So every node can be queried from the front end. You have now a good scalability on the front end. You can have a load balancer and load balance all of the nodes. And still, on the back end, they can go back and know which node to ask for this. When I said that the bottom level has the specific partition, I lied a little bit, because it's not the node number. Roxy uses multicast. So nodes, when they have a partition of the data, they subscribe to a multicast channel. What you have in that top level is the number of the multicast channel that will handle that partition. That allows us to make Roxy nodes more dynamic and handle also the fault tolerance situations where nodes go down. Well, it doesn't matter if you send a message to a multicast channel. Any node that is subscribed to a multicast channel will get that message. Which one to respond? Well, it will be the faster node, the node that is less burdened by other queries, for example. And if any node dies in that channel, it really doesn't matter. You're not stuck in a TCP connection waiting for the handshake to happen because the node went away. It is UDP, you just send the message and you will get the response. And of course, if nobody responded in a reasonable amount of time, you can resend that message as well.
Going back to the architecture of the system and the fact that how long it's been in development and in use, and the massive changes that have occurred at the industry level as far as how we approach data management and the uses of data and the overall systems that we might need to integrate with, I'm curious how the HPCC platform itself has evolved accordingly, and some of the integration points that are available for being able to reach out to or consume from some of these other systems that organizations might be using.
We have changed quite a bit. So even though the HPC Systems name and some of the code base is resembles what we had 20 years ago, as you can imagine, any piece of software is a living entity, and changes and evolves and adapts. Of course, as long as the community is active behind it, right? So we have changed significantly. We have not just added functionality, core functionality to HPC, or changed the functionality that it had to adapt to times, but also build integration points. I mentioned Spark, for example, and Spark, even though HPCC is very similar to Spark, Spark has a large community around machine learning. So it is useful to integrate with the Spark, because many times people might be using Spark ML, but they might want to use HPC for data management. And having a proper integration where you can run a Spark ML on top of HPC is something that can be attractive to a significant amount of the HPC open source community. Other cases, like for example Hadoop and HDFS access, are the same way. Integrations with other programming languages. Many times people don't feel comfortable programming everything in ECL, and ECL works very well for data management, something that is a data management centric process. But sometimes you have little components on that process, for example, that cannot be easily expressed in ECL, or at least not in a way that is efficient. I don't know. I'll just throw one. Let's say that you need to generate unique IDs for things, and you want to generate these unique IDs in a random manner, like UUIDs. Surely you can code this in ECL. I can come up with some crafty way of doing it in ECL, but it would make absolutely no sense to code it in ECL to then be compiled into some big chunk of C++ when I can code it directly in C or C++ or Python or Java or JavaScript. So being able to embed all of these languages into ECL became quite important. So we built quite a bit of integration for embedded languages. Is back even a few major versions ago, a few years ago, we had support for, I mentioned some of these languages already, Python and Java and JavaScript. And of course, C and C++ was already available before. So people can add these little snippets of functionality, create attributes that are just embedded language type of attributes. And those are exposed in ECL as if they were new ECL primitives. So now they have the ability of this uh, expandability of the core language to support new things without needing to write them in ECL natively every time. And there are plenty of other enhancements as well on the front end side. So I mentioned ESP. ESP is this front end access layer. Think of it as some sort of message bus in front of your Roxy system. In the past, we used to require that you code your ECL query for Roxy, and then you need to, and ESP is also coded in C++. So you need to go to ESP and extend ESP with a dynamic module to support the front-end interface for that query, which is twice the work. And you require someone that also knows C++, not just someone that knows ECL. So we changed that, and we use something now that is called dynamic ESDL that auto-generates, as I mentioned before, these interfaces from ESP as you code these queries in ECL. All they'll expect that you will code the query with some parameterized interface to the query, and then automatically ESP will take those parameters and expose those in this front end interface for users to consume directly. We also have done quite a bit of integration in systems that do that can help with the benchmarking of HPCC, availability monitoring, and performance monitoring, all of the uh, capacity planning of HPC as well. So we try to integrate as much as we can with other components in the open source community. We truly love open source projects. So if there is a project that already has done something that we can leverage, we try to stay away from reinventing the wheel every time we use it. If it's not open source, if it's commercial, we do have a number of integrations with commercial systems as well. We are not we are not religious about it, but certainly it's a little bit less enticing to put the effort into something that is closed source. And again, we believe that the model in open source is a very good model, because it gives you the ability to know how things are done under the hood and extend them and fix them if you need to. We do this all the time with other projects. We believe that it has a significant amount of value for anyone out there.
On the subject of the open source nature of the project, I know that it was released as open source in, I think you said, the 2011 timeframe, which postdates when Hadoop had become popular and started to accrue its own ecosystem. I'm curious what your thoughts are on the relative strengths of the communities for Hadoop and HPCC currently, given that there seems to be a bit of a decline in Hadoop itself as far as the amount of utility that organizations are getting from it. But also, I'm interested in the governance strategy that you have for the HPCC platform and some of the ways that you approach sustainability of the project.
So you're absolutely right. The Hadoop community has apparently at least reached a plateau. It is far larger than HPC systems community in number of people. Of course, it was the first to the open source. So we had HPC for a very long time. It was closed source. It was proprietary, and we didn't. Um, at the time, we believed that it was so core to our competitive advantage that we couldn't afford to release it in any other way. When we realized that reality, the core advantage that we have is on one side data assets, and on the other side is the high level algorithms. We knew that the platform would be better sustained in the long run. And sustainability is an important factor for the platform and for us, because the platform is so core to everything we do that we believe that making it open source and free, completely free, as both not just a freedom of speech but also free beer. We thought that that would be the way to ensure this long-term survivability and development and expansion and innovation in the platform itself. But when we did that, it was 2011, so it was a few years after Hadoop. Hadoop, if you remember, it started as part of another project around web crawling and web crawling management, which eventually ended up as its own top level Apache project in 2008, I believe. So it was already 3 or 3.5 years after Hadoop was out there, and the community was already large. There is, so over time, we did gather a fairly active community, and today we have an active, very technical, deeply technical community that not just helps with extending and expanding HPCC, but also provides ideas, use cases, sometimes interesting use cases of HPCC, and uses HPC in general and regularly. The HPC systems community continues to grow. The Hadoop community seems to have reached a plateau. Now, there are other communities out there which also handle some of the data management aspects with their own platforms, like Spark, I mentioned before, which seems to have a better performance profile than what Hadoop has. So it has been also gathering active people in those communities as well. I think open source is not a zero-sum game where if a community grows, the other one will decrease, and then eventually the total number of people in the community will be the same across all of them. I think every new platform that introduces capabilities to open source communities and introduces new ideas and helps develop apply innovation into those ideas is helping the overall community in general. So it's great to see communities like the Spark community growing, and I think there is an opportunity, and many of the users in both communities are using both at some point, for all of them to leverage what is done in the others. Surely, sometimes the specific language used in coding the platforms makes a little bit of creates a little bit of a barrier. Some of these communities are now, just because of the way Java is potentially more common, they use Java instead of C++ or C. So you see that sometimes the people that are in one community who might be more versed in Java feel uncomfortable going and trying to understand the code in the other platform that is coded in a different language. But even then, at least some general ideas in the algorithms and the functions and capabilities can be extracted and used in the other. And I think this is good for the overall benefit of everyone. I see, in many cases, open source as an experimentation playground where people can go there, can bring new ideas, apply those ideas to some code, and then everyone else eventually leverages them because these ideas percolate across different projects. It's quite interesting. Having been involved personally in open source since the early '90s, I'm quite fond of the process open source works. I think it's beneficial to everyone in every community.
And in terms of the way that you're taking advantage of the HPCC platform at LexisNexis and some of the ways that you have seen it used elsewhere, I'm wondering what are some of the notable capabilities that you're leveraging and some of the interesting ways that you've seen other people take advantage of it?
That's a good question, and the answer might take a little bit longer. So in LexisNexis in particular, certainly we use HPCC for almost everything we do, because almost everything we do is data management in some way and data querying. Now we have interesting approaches to things. Is we have a number of processes that are done on data. One of those is this probabilistic linkage process, and probabilistic linkage requires sometimes quite a bit of code to make it work correctly. So there was a point where we were building this in ECL, and it was creating a code base that was getting more and more sizable, larger, bigger, less manageable. So at some point, we decided that that level of abstraction, that is pretty high anyway in ECL, wasn't enough for probabilistic data linkage. So we created another language. We called it Salt, and we didn't release that language as open source, by the way. It's still proprietary. But that language is a language that is, you could consider it a domain specific language for data linkage, probabilistic data linkage, and data integration. So that compiler for Salt compiles Salt into ECL, and the ECL compiler compiles ECL into C++, Clang, or GCC compiles it into assembler. So you can see how abstraction layers are like layers in an onion. Of course, every time you apply an improvement, an optimization in the ECL compiler, or sometimes the GCC compiler team applies an optimization in GCC, everyone else on top of that layer benefits from the optimization, which is quite interesting. We liked it so much that eventually we had another problem, which was dealing with graphs. And when I say graphs, I mean social graphs rather than charts. So we built yet another language that deals with graphs and machine learning, and particularly machine learning in graphs, which is called KEL, or Knowledge Engineering Language, which, by the way, we don't have an open source version, but we do have a free version of the compiler out there for people that want to try it. So KEL also generates ECL, and ECL generates C++, and again, back to the same point. So this is an interesting approach to building abstraction by creating DSLs, domain-specific languages, on top of ECL. Another interesting application of HPCC outside of LexisNexis is there is a company that is it's called Guard Hat. They do hard hats that are smart. They can do geofencing for workers. They can do detection of risky environments in manufacturing environments, or in construction. So they use HPCC, and they use some of the real-time integration that we have with things like Kafka and CouchDB and other integrations. I mentioned that we have worked actively on integrating HPC with other open source projects to essentially manage all of this data, which is fairly real time, and create these real time alerts and real time machine learning execution for models that they have, and integration of data, and even visualization on top of it. And there are more and more. I could go for days giving you some of the ideas there of things that we have done, or others in the community have done using HPCC.
And in terms of the overall experience that you have had working with HPCC on both the platform and as a user of it, what have you found to be some of the most challenging aspects and some of the most useful and interesting lessons that you've learned in the process?
That is a great question, and I'll give you a very simple answer, and then I'll explain what I mean. Some of the biggest challenges, if you're a new user, is ECL. Some of the biggest benefits are ECL. Unfortunately, not everyone is well versed in declarative programming models. So when you are exposed for the first time to a declarative programming language that has immutability and laziness and no side effects, it makes sometimes a little bit of a brain twister in some way, right? You need to think the problems in a slightly different way to be able to solve them. When you instead are used to imperative programming, you typically solve the problem by decomposing the problem into just a recipe of things that the computer, this processor needs to do step by step, one by one. When you do declarative programming, you decompose the problem in a set of functions that need to be applied, and you build it from the ground up. It's a slightly different type of, 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 of approach, but once you get the idea of how this works, it becomes quite powerful for a number of reasons. It becomes quite powerful because, first of all, you get to understand the problem more, and you can express the algorithms in a far more succinct way. Algorithms end up being just a collection of attributes, and some of these attributes depend on other attributes that you have defined. It also helps you with better encapsulate the components in the problem. So now your code, instead of becoming just some sort of spaghetti that is hard to troubleshoot, is well encapsulated, both in terms of functional encapsulation and also data encapsulation. So if you need to touch anything later on, you can touch it safely without needing to worry about what this function could be doing that I'm calling here. Do I need to go and also look at that function? Because there are no side effects. And it also gives you the ability to if you, of course, as long as you name your attributes correctly so people understand what they are attempting to do, or they are supposed to do, you can collaborate more easily with other people as well. So after a while, I realized that I was building code in ECL, and others have also the same way. Then realized that the code that they write in ECL is, first of all, mostly correct most of the time, which is not what you do when you have a non-declarative code programming, and that you know that if the code compiles, there is a high chance that the code will run correctly, and it will give you correct results after it runs. Unlike, as I was explaining before, when you have dynamically typed languages in imperative programming with side effects, where, yeah, surely the code might compile and maybe it will run fine a few times, but one day it might give you some sort of runtime error because some type is mismatched or some side effect that you didn't consider when you re-architected some piece of the code now is kicking in and getting your results different from what you expected. I think again, ECL has been really quite quite a blessing from that standpoint. But of course, it does require that you learn this, you want to learn, and you learn this new methodology of programming, which could be similar to what someone that knows Python or Java needs to learn in order to apply SQL. And SQL, again, is another declarative language, so you don't code SQL imperatively when you are trying to query a database.
Looking forward in terms of the medium to long term, as well as some of the near term for the HPCC platform itself, what do you have planned for the future, both in terms of technical capabilities and features, but also as far as community growth and outreach that you'd like to see?
So from the technical capabilities and features, we tend to have a community roadmap of things, and try to, as much as we can, stick with those roadmaps. So we have some these big ideas that tend to get into the next or the following major version. These smaller ideas that are typically non-disruptive and don't break past compatibility, that go into the minor versions, and then of course these bug fixes. Um, and like many say, they are not bugs but opportunities. But in the in the big ideas side of things, some of the things that we've been doing is doing better integration. As I mentioned before, integration with other open source projects is quite important. We've been also trying to change some of the underlying components in the platform. There were some components that we have had for a very, very long time, like, for example, the underlying communication layer in Roxy and Thor, that we think they might be ripe now for a revamping by incorporating some of the standard communication layers out there. There is also the idea of making the platform far more cloud friendly, even though it does run very well in any public cloud, and OpenStack, and Amazon, and Google, and Azure. But we want to also make the clusters more dynamic. I don't know if you spotted when I said that, when I explain how you do data management with HPCC, and they said, well, you have a 10 node Thor. Well, what happens when you want to change that 10 node Thor and make it a 20 node Thor or a 5 node Thor? Maybe you have a small process that would work fine with just a couple nodes or one node, and you have a large process that might need 1,000 nodes. Today, you can't dynamically resize the Thor cluster. Surely you can you can resize it by hand and then do a redistribute of the data, and now have the data in the number of nodes that you have. But it is a lot more involved than we would like to see. With dynamic cloud environments, the elasticity becomes quite important, because that's one of the benefits of cloud. So making the clusters also more elastic, more dynamic, is another big goal. Certainly, we continue to develop machine learning capabilities on top of it. We have a library of machine learning functions out there, algorithms, methods, and we are expanding that. We sometimes add even some of these machine learning methods, which are quite, I would say, innovative. One of our core developers and also researchers developed a new distributed algorithm for k-means clustering, which she hasn't seen in the literature before. So it's part of one a paper and her PhD dissertation, which is very good, and the other one is also part of HPCC now. So now people can leverage this, which gives a significantly higher scalability to k-means, particularly if you're running a very large number of nodes. I don't want to get into the details on how it creates this far better performance, but in some it distributes the data less, and instead it distributes the centroids more, and it uses the associative property of the k-means, the main loop of k-means clustering, to try to minimize the number of data records that need to be moved around. That's from the standpoint of the roadmap and the platform itself. On the community side, we continue to try to expand the community as much as we can. One of our core interests is to get, I mentioned this core developer who is also a researcher. We want to get more researchers and academia on the platform. We have a number of initiatives, collaboration initiatives, with a number of universities in the US and abroad. Universities like Oxford University in the UK, University College London, Humboldt University in Germany, and a number of universities in the US, like Clemson University, Georgia Tech, and Georgia State University. And I could. So we want to expand this program more. We also have an internship program. We believe that one of the things that ancillary goals that we want to achieve as well with the HPCC systems project, open source project, is to also help balance better the community behind it, from balancing diversity across the community. So attracting both in general, gender diversity and racial diversity and background diversity. So we are trying to also put quite a bit of emphasis in students, even high school students. So we are doing quite a bit of activity with high schools. On one side, trying to get them more into technology, and of course, learn HPCC. But also on the other side, try to also get more women into technology, get more people that otherwise wouldn't get into technology, because they don't get exposed to technology in their homes. So that's another core piece of activity in HPCC, in the HPC community. And last but not least, as part of this diversity, there are certain communities that are a little bit more disadvantaged than others. One of those is people in the autism spectrum. So we have been doing quite a bit of activity with organizations that are helping these people. So also trying to enable them with a number of activities, and some of those have to do with training them into HPCC systems as a platform and data management to give them open opportunities for them for their lives. Many of these individuals are extremely intelligent. They're brilliant. They might have other limitations because of their conditions, but they would be very, very valuable resources, not just for LexNext resolutions. Ideally, we would hire them, but even for other organizations as well.
Yeah, it's great to hear that you have all of these outreach opportunities as well for trying to help bring more people into technology as a means of giving back, as well as a means of helping to grow your community and contribute to the overall use cases that it empowers. So, for anybody who wants to follow along with you or get in touch, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think there are a number of gaps, but the major one is many of the platforms that are out there tend to be quite clunky when it comes to integrating things. Unfortunately, we are at the point where we are not. I don't think we are mature enough. So, and mature enough, I mean, if you are a data management person, you know data very well, you know data analytics, you know data process, but you don't necessarily know operating systems. You don't know. You are not a computer scientist that can deal with data partitioning and computational complexity of algorithms in partition data, and there are many details that are unnecessary for you to do your job. Should be unnecessary for you to do your job correctly, but unfortunately today, because of the state of things, many times many of these systems, commercial and non-commercial, force you to take care of all of these details or assemble a large team of people from system administrators to network administrators to operating system specialists to middle layer specialists until you can build a system that can you do your data management. And that's something that we do try to overcome with HPC, giving this creating this homogeneous system that you deploy with a single command and that you can use a minute later after you deployed it. I don't say that we are in the ideal situation yet. I think there is still much to improve on, but I think we are a little bit further along than many of the other options out there. If you know the Hadoop ecosystem, you know how many different components there are out there, and you know, if you have done this for a while, you know that one day you realize that there is I don't know, a security vulnerability in one component, in pig, and now you need to update that. But in order to update that, you're going to break the compatibility of the new version with something else, and now you need to update that other thing, but there is no update for that other thing because that thing depends on another component. So yeah, and this goes on and on and on. So having something that is homogeneous, that it doesn't require for you to be a computer scientist to deploy and use, and that it truly enables you at the abstraction layer that you need, which is data management, is a significant limitation of many systems out there. And again, not just pointing this at open source projects, I'm also commercial projects as well. I think it's something that some of the people that are designing and developing the systems might not understand because they are not the users, but they should think as a user. You need to put yourself in the shoes of the user in order to be able to do the right thing. Otherwise, whatever you build is pretty difficult to apply, and sometimes it's even useless.
Well, thank you very much for taking the time today to join me and describe the ways that HPCC is built and architected, as well as some of the ways that it's being used both inside and outside of LexisNexis. So I appreciate all of your time and all of the information there. And it's definitely a very interesting system and one that looks to provide a lot of value and capability. So I appreciate all of your efforts on that front, and I hope you enjoy the rest of your day.
Thank you very much. I really enjoy this, and I look forward to doing this again. So one day we'll get together again. Thank you.